From the clippings, we have seen the path of the cartwheel and spoke of the wheel are perpendicular. The path, this is the path of the wheel, and this is the spoke of the wheel. So this is the radius, and path is a tangent. And path is a tangent. So, radius and tangent are perpendicular. We have seen radius and tangent perpendicular at the point of contact, and this is the point of contact. So we go to our theorem, the theorem 40. Now statement of the theorem 40. Statement of the theorem is that the tangent to a circle, at any point on it is perpendicular to the radius passes through the point of contact. Radius and tangent are perpendicular at the point of contact. Now this is statement of the theorem. At first we draw the figure of the theorem. First we draw a circle and radius of the circle. This is radius of the circle. This is the point O, and draw a tangent. Sorry, this is the radius, and this point we draw a tangent. This point is P, and at the point P we draw a tangent. This is the tangent AB. So now this is now given. O is the center of the circle and OP is a radius, and AB is a tangent at the point P. Given AB is a tangent at the point P of a circle with center O, and OP is radius to the point P. Required to prove OP and AB are perpendicular. OP and AB are perpendicular. OP perpendicular to AB. Construction. Any other point Q is taken on the tangent AB. Any other point Q except P. Take Q is any point on AB other than P and join O and Q. Now this is the point Q. This is the point Q, and join O and Q. And this line segment intersect the circle at a point R. Now proof of the theorem. Now proof. Any other point on AB except P is outside the circle. Any other point on AB other than P is outside the circle. Now, because P is the point on the circle and AB is a tangent, so any other point on AB is outside the circle. So definitely the distance between center to outside the point and radius of the circle must be less than this distance. So therefore, here OQ is the distance from O to outside point Q. So therefore OQ intersects the circle at the point R. Let R be the point of intersection. Therefore OR is less than OQ. OR is less than OQ, as R is the point between O and Q. R is the point between O and Q, so OR less than OQ. So therefore, again OR equals to OP, because both are radii of a same circle. We know radii of a same circle are all are equal, so OR equals to OP. So therefore, OP less than OQ. Now, as the point Q is any point on AB, Q is an arbitrary point. Q is arbitrary point. So if OP is the least distance from O to the AB, OP is the least distance. The OP is the least of all the line segments drawn from the center O to the tangent AB. Again we know, again the least distance is the perpendicular distance. Least distance is a perpendicular distance. So OP is perpendicular to AB. So OP is perpendicular to AB. Now this is the proof of the theorem. This is chapter 15.1. Next we will do exercise of this chapter.